Hi my dear students, today we will learn about application of Gauss's law. Now previous classes we learned about Gauss's law and there we studied that the flux due to an electric field through a closed surface is given by the surface integral of electric field is equal to charge enclosed by the surface by epsilon 0. This is called Gauss's law. We can use Gauss's law to find out electric field for a system which has some type of symmetry. Then we can easily find out the electric field. So in this section we can check certain systems which have some type of symmetry. Okay. So here is the first example. Find the electric field outside a uniformly charged solid sphere. Okay, uniformly charged solid sphere of radius capital R and total charge Q. Okay, total charge Q. This is the problem. Now we can draw a solid sphere here like this. Suppose this is the solid sphere, okay, whose radius is given that capital R. This is capital R, and this sphere is uniformly charged with charge Q. Okay. Now we have to find out electric field some other point P. Suppose this is the point. We have to find out electric field at this point P due to this uniformly charged sphere of radius capital R. Okay, this is the question. Now suppose we can assume another sphere. Okay, another sphere whose radius is smaller. Okay, suppose this is the distance smaller. Okay, so we assume a spherical Gaussian surface. Okay, spherical Gaussian surface. Gaussian surface. Okay, whose radius smaller, which is greater than radius of solid sphere, capital R. Okay, so due to the spherical symmetry of the problem, it is given that we have a charged solid sphere. So we assume a Gaussian surface with the same symmetry. Okay, so a sphere, we assume a Gaussian sphere. And now we want to find out the electric field at the point P. Okay, so now this P is lying on the surface of the Gaussian sphere. Okay, this Gaussian sphere has radius smaller. This is the distance from this center to this point P. Okay, now we can apply this Gauss law on this sphere, this Gaussian sphere. Okay, so here the closed surface means Gaussian sphere. Okay, so this E dot ds, okay, this is equal to, I think we used earlier A for this aerial element, so I can write here also small a, E dot dA. Okay, now you can see that since this Gaussian sphere, the electric field is always outward to this, radially outward, right? Because our problem is a uniformly charged solid sphere. Okay, so this electric field is always radially outward. And this surface area of the sphere is also pointing radially outward. So you can write this expression by removing this dot product like this, mod E dot dA. Okay, since it is given that this solid sphere is uniformly charged, we can write this electric field outside this integral, because this should be uniformly charged electric field, right? So you can take it outside this part. So this gives you mod E dA. Okay, we assume a sphere, so this aerial element is also on the surface, some aerial element of the Gaussian sphere. Okay, so this integral gives you area of the Gaussian sphere. So you can write this as mod E 4 pi r square. This r is the radius of the Gaussian sphere, right? Okay, now this should be equal to the charge enclosed by the surface by epsilon 0. What is the charge enclosed by the surface? It is given that the total charge of the uniform solid sphere is Q. Okay, so you can write here Q by epsilon 0. Okay, so you can see that the electric field, the magnitude of the electric field at point P, which lies on the Gaussian surface, is given by Q by 4 pi epsilon 0 r square. Okay, in vector form this electric field is radially outward, so you can write this as electric field equal to Q by 4 pi epsilon 0 r square r cap. So without any integration, we can find out the electric field outside a uniformly charged solid sphere using this Gauss law. Okay, the electric field due to the solid sphere appears, electric field outside a solid uniformly charged solid sphere appears just like electric field due to a point charge. This electric field gets reduced by 1 by r square as this point moves away from this uniformly charged sphere. Okay, now as a second example, we can do the problem in the case of a uniformly charged cylinder. Find electric field inside a long wire whose charge density is proportional to distance from the axis. Distance from the axis. Okay. That means this rho can be equal to Ks, where K is proportionality constant. Okay, proportionality constant. This is the problem. Now, suppose this is the long cylinder. Long wire. Okay. Now we assume a Gaussian cylinder here. Suppose this is the Gaussian cylinder. Because we want to find out electric field inside the wire. Okay, this is wire, this is our Gaussian cylinder. Since this system has cylindrical symmetry, we use a cylinder, Gaussian cylinder. Okay, Gaussian surface as a cylinder. Now, the distance from this point to this radius of this Gaussian cylinder is assumed as S. Okay, this is S. Now, Gaussian surface. A cylinder, due to the cylindrical symmetry, it is a cylinder. Okay, a cylinder whose radius is S. Okay. Now, we know that as this is the axis of the wire. Okay. As the charge density varies from this to this point, proportional to this way. Okay, suppose this is, for example, here we assume Gaussian surface like this. Here, as we move from this axis to the surface of this cylinder, this Gaussian cylinder, the charge density varies like this, rho equal to Ks. Okay, now we already learned that by Gauss law, surface integral of E dot dA equal to Q enclosed by epsilon 0. Okay, here the closed surface is assumed in the form of a cylinder. Okay, Gaussian surface is a cylinder. Now we want to find out the Q enclosed by this cylinder. Okay, so this is the surface. Okay, so now we have to find out the charge enclosed by this Gaussian cylinder. Okay, so in this case we have to find out Q enclosed. Okay, Q enclosed is given by surface integral. This time I can put what I want to represent is this is over the Gaussian surface. Okay, this is over the Gaussian surface. So in this case we have to find out the charge enclosed. Okay, charge enclosed, that means we have to find out integral rho d tau. Okay, integral rho, what is this rho? Rho is given by charge density. Okay, since this system has cylindrical symmetry, we have to use this volume element in cylindrical coordinates. Okay, cylindrical coordinates. So for our convenience, I can write this d tau here. I will show you here. D tau equal to S prime ds prime dz d phi. Okay, I put S prime just to distinguish this coordinate by this S, radius of our Gaussian surface. Okay, now we can integrate over this, then only you get this charge enclosed by this surface. Okay, now let length of the Gaussian cylinder is L. Let length of the cylinder is L. Okay, length of this cylinder is L. Now I can integrate this thing. What are the limits for these coordinates? Phi varies from 0 to 2 pi. Z varies from 0 to L because Z is along this axis. This is the length coordinate, and S prime varies from 0 to S. Okay, so I can find out the integral using this. Okay, what I get then? Q enclosed equal to volume integral of rho is given by this expression, but this time this S, I want to replace this S by S prime, K S prime, because you know that this S lying on the surface of this Gaussian cylinder, right? So in order to take a small variable as a variable, this S as a variable, I put S prime here. So K S prime. Now d tau is given by this expression. This is volume integral. So S prime, ds prime, dz, d phi. Now dz d phi gives you 2 pi L, right? Dz d phi gives you 2 pi L, and now you get here 2 pi L. This integral gives you 2 pi L, 2 pi L K. Okay, 2 pi L K integral S prime square ds prime. So it gives you S prime q by 3, integration running from 0 to S. Okay, so you get here, this is equal to 2 pi L K S cube by 3. Okay, what is this? This is charge enclosed. Now, how you get this electric field? That means, now you get here I think you get what is meant by this charge enclosed by this Gaussian cylinder is given by this expression. Now you can apply this to this Gauss law. Okay, so I think I can write here. Okay, so here along this surface of the cylinder, curved surface of the cylinder, this integral, surface integral mod E dA, because you know that both electric field and the aerial vector pointing along same direction. So you get like this. This is equal to 2 pi L K S cube by 3 epsilon 0, because Q enclosed by epsilon 0. Okay, so this is equal to mod E surface integral of dA. What is this surface area of this curved surface? It is given by 2 pi Ls. So this is equal to mod E 2 pi Ls. Okay, 2 pi Ls. So this gives you mod E equal to, what you get here, 2 pi Ls cancels out, you get here K square by 3 epsilon 0. Okay, what about the surfaces of this curved surface at both ends? At these both ends, the electric field and the surface area are mutually perpendicular. Okay, electric field and the aerial vector are mutually perpendicular, so they cancel out, and so you get only this thing, K square by 3 epsilon 0. This electric field is pointing along S direction, so you can write it in vector form as E equal to K square by 3 epsilon 0 S cap. Okay, K S square by 3 epsilon 0 S cap. This is the electric field inside a long cylinder. Okay. A third example, we can consider a system with planar symmetry. For example, consider an infinite plane. Okay. Consider an infinite plane whose surface charge density is sigma. Find the electric field. Okay, find the electric field. Suppose this is the infinite plane, then the electric field from the upper surface it is like this, for the down surface it is like this. Okay. Now, due to the planar symmetry of the problem, this is our Gaussian pillbox whose area is given by A. Okay. Similarly, it is given that the surface charge density of this infinite plane is sigma. Okay. Now, I can write here the Gaussian surface is a pillbox. Okay, rectangular pillbox whose area is assumed as capital A. Okay, this is the area. Now you can apply Gauss law, because Gauss law is applying over this Gaussian surface, Gaussian pillbox, and now you know that the electric field is pointing, okay, electric field is pointing outward from this plane sheet. So, for the upper surface, the electric field and aerial vector pointing along the same direction, and so you can write here this E dot dA as mod E dA. Okay. Now we can see that here both the sides of this pillbox, the electric field and aerial vector are mutually perpendicular, and so they are cancelled out. We have only this upper and lower surfaces in this case. Okay, so you can write here this is equal to 2 mod E A. Okay, area of the upper surface and its opposite surface. All other sides, the E dot dA are mutually perpendicular, and so they cancel out. Okay, now this is equal to Q enclosed, okay, by epsilon 0. Q enclosed by epsilon 0. What is this Q enclosed? Because already given that the plane has surface charge density sigma, so this is equal to sigma into area of the pillbox, sigma A by epsilon 0. Okay, now you can simplify this thing, that is you get that mod E equal to sigma by 2 epsilon 0. Okay, in vector form you can write this as E equal to sigma by 2 epsilon 0 n cap. That means the electric field is pointing perpendicular to the plane sheet. Okay, like this. What is the peculiarity of this electric field? You can see that actually if this sigma, the sigma represent uniform surface charge density. This means that the electric field due to an infinite plane is a constant. As you move away from this infinite plane, the effect of more area of the plane included in that point. There is no other change. So there is no influence of the distance from where you have to find out the electric field. Electric field due to an infinite plane is a constant. It is given by sigma by 2 epsilon 0 n cap. Okay, so as an application to Gauss's law, we discussed here three types of symmetry. As a spherical symmetry, we assume a uniformly charged solid sphere. For a cylindrical symmetry, we assume a long wire, okay, infinitely long wire, and in this case we assume an infinite plane sheet, okay, infinite plane sheet. If the plane sheet is infinite, there is no dependence on where we have to find out the electric field. Okay, it's a constant, sigma by 2 epsilon 0 n cap. Okay. As a fourth example, consider two infinite parallel planes. Okay, two infinite parallel planes. They carry uniform charge density but with equal and opposite charge densities. Okay, equal and opposite charge densities plus or minus sigma. Okay, find the electric field case 1. Now, suppose this is the plane sheets, infinite sheets. Okay, there are two sheets like this, infinite sheets. This is with positive charge plus sigma and this is with minus sigma. Okay, so we already learned that the electric field, suppose this is the sheet 1, this is sheet 2. Okay, so the electric field due to sheet 1 along this direction E1. Okay, similarly electric field due to minus charge is always pointing towards this sheet, so this is like this E2. This is region 1. Suppose this is region 1. This is region 2 and this is region 3. Okay. Now in this region 2, electric field due to the first sheet, that is with the positive charge, the electric field is pointing along this direction. This is E1, moves away from the positive charge. And here the electric field due to the second sheet, which one has negative charge, pointing towards the sheet like this. Okay, this is E2. Now for this region 3, this electric field due to this sheet 1 is points like this E1. This is E1. And electric field due to this sheet 2 points towards the sheet. like this. E2. So what we get here from this diagram itself, already we see that equal and opposite charges, plus sigma and minus sigma. So what happens here? Here the E1 and E2 both has same magnitude, right? Mod E1 equal to mod E2. Okay, both are equal. And what is its value? Now previous problem we already find out that this is equal to sigma by 2 epsilon 0. Okay. Now for this region 1, both E1 and E2 are opposite, equal and opposite. So for region 1, this cancels out and the electric field is equal to E1 plus E2 equal to 0. Okay. Now for region 2, both the electric fields are points in the same direction. So you have here E equal to E1 plus E2. Okay. This is equal to sigma by 2 epsilon 0 plus sigma by 2 epsilon 0. This gives you sigma by epsilon 0. Okay. At the same time, in region 3, this electric field is equal to E1 plus E2. But this time, both are equal and opposite. So you get here 0. So what is our conclusion? We can see that the case of two infinite parallel planes with same surface charge density but with opposite polarity, that means positive charge in one sheet and negative charge in the other sheet, but both are magnitude, equal magnitude. In that case, electric field exists only in between the plane sheets. Okay, that is given by sigma by epsilon 0. Okay, so now you can use this, you can do problems using Gauss's law, which helps you find out electric field easily without doing integration. If your system has some type of symmetry, you can extend the problems using, we already find out spherical symmetry, cylindrical symmetry and planar symmetry. You can extend this type of symmetries to the given problem and find out easily electric field due to the charge distribution. Okay, that is the power of Gauss's law. So do more problems and happy learning. Thank you.